In the next several lectures, we're going to talk about some of the fundamental properties of fluids that will ultimately describe how a particular fluid responds to changes in its environment. But before we do that today, I want to talk a little bit about how we're going to define properties. And the first thing we need to do is think about in what context we're going to describe them. And that's where we're going to employ the continuum approach. The second thing we need to talk about is the state of the fluid. And the state of the fluid describes how the property of the fluid at a particular moment in time relative to other environmental conditions such as temperature and pressure. And then finally, we're going to talk a little bit about two different types of properties, extensive properties and intensive properties, and which of those we tend to use more often in fluid mechanics. So let's get started. The first thing we're going to do is look at the continuum approach. And when we have a volume of air here that we want to describe, and in the volume of air are billions and billions and billions of individual molecules. And so one approach we could take is to define the properties of every individual molecule. So if we look at that paper, we have all these different molecules, and what we're going to do is define the chemical structure and how all those different molecules are going to interact with every other molecule, and how that ultimately determines how this gas interacts and changes when we change the temperature, the pressure, or the flow speed and things like that. And you can immediately see that's pretty impractical. Even with these dots that I did, I had to put dots on the screen the entire semester, and I wouldn't have enough to even describe this little volume of air right in here in front of us. So what's commonly done in engineering is that we, instead of defining every little molecule, we create bulk properties that represent the interactions of all the little molecules, but give us some measure of something that we intuitively understand. So we change that into some fluid mass. And we do this in statics. You've done this in several of your other classes, where if you have a cantilevered beam of wood and you put a weight on the end of it, we don't go through and describe every single cell or every single molecule in that beam of wood. We measure things like the strength of that wood, the Young's modulus, and some other properties of it that allow us to make estimates and calculations of how much stress that beam can entail before it might break. But it really is individual molecular interactions, but we don't necessarily care about those, so we describe some other bulk property that describes how that particular beam interacts with its environment. And we're going to do the same thing with fluids. And doing that is what's again called the continuum approach, where we replace the individual molecules with a continuous medium called a continuum. And it is a very practical way of dealing with most engineering problems. There are a few cases where that doesn't work very well, and examples are high altitude flight, where individual molecules are so far apart that describing a continuum really doesn't make sense. We can't actually, there's so few molecules and there's so much distance between them that we can just describe the molecules as needed. The second situation is in very small and microscale or nanoscale flows, where the size of the molecule might be the same size as the vessel it's flowing through, and so we only have one molecule passing at a time, and so we can just describe individual molecules. And so then the continuum approach again doesn't really work very well. Might as well just describe the individual molecules as they pass our field of view or what we're interested in. But again, for most applications, and in all of the ones in this class, the continuum approach is a very practical and useful way to describe the fluid properties. Okay, so the next thing we need to think about is the state or condition of a fluid at a particular time, the fluid state. And a fluid state really defines what a particular property might be for that particular fluid given the environmental conditions around it, given the temperature and the pressure. And a really good example of that is density. Density is given by the Greek symbol rho, is equal to mass over volume, where I do a cross through the V to indicate volume as opposed to V for velocity, which we'll use later in the semester. And it is some function of temperature and pressure. There's some other things that come in, like salinity, that if we add volume mass to a fluid, the density can go up. But for now, if we're not adding something else, the density is a function of temperature and pressure. And that's what we call an equation of state. So for a temperature for a particular gas or liquid, a particular fluid. We have a temperature and a pressure. If we know those two, we can figure out the density. And if we look, say, at water at negative 20 degrees Celsius is a solid, right? At 40 degrees Celsius is a liquid, and at 200 degrees Celsius is a gas. Okay? And so that describes the equation of state, or the density of water at different temperatures. And so a solid or ice is slightly less dense than water at, say, 4 degrees Celsius. So as the temperature increases from minus 20 to 4, the density is actually going up. It reaches 4 degrees Celsius, and as it continues to warm, the density goes back down. So it doesn't have to be a linear relationship, but there is a relationship between the fluid density and the temperature here. Okay? Finally, before we get into the specific different types of fluid properties, density being one that we'll talk in much greater detail in the next video, we want to talk about how the two different types of properties and the contexts in which we define the types of properties. And so the first one we want to look at are extensive properties. And these describe the total bulk of the fluid. And examples of these are mass and volume. And the reason these are considered extensive properties is because we have this volume of air in front of us, right? It has a very particular mass, a very particular volume. If we make it a little bigger, then that volume changes and that mass changes. And so it really describes this very particular volume of air that we have in front of us. If we move over somewhere else, or we define this little volume of air here, it has a different mass and a different volume. And so extensive properties aren't very portable, although they're really good for, say, weighing an individual in a medical sense. We don't typically use them in fluid mechanics because they don't apply to different situations. They only apply to this one particular bulk of fluid that we've defined. Instead, we often use what we call intensive properties, and those describe a small volume on a per volume basis. And examples of those are one we've already talked about, is density. Again, is mass over volume, and has the units of grams per centimeter cubed. Where now we're describing the mass relative to a small volume, so some unit volume. And that's nice because the density of water, fresh water, at a particular temperature is going to be the same anywhere you go in the world. No matter how big your volume is of water that you're describing or how small, it's going to be the same as long as the temperature doesn't change. And so we can tabulate those things. We can tabulate water over temperature and list all the densities, and if you open your textbook, you can see those. And no matter where you are in the world, you open that density is the same. So now we have a very portable definition by using density as opposed to mass, where it would change for however much water we have. Another intensive property is concentration. And we can talk about that a little bit more. We don't deal with it a whole lot in this class, but again, it's also like moles per volume or mass per volume. So it's defined similarly, and it's a concentration. So if we have a fluid that has a concentration, we don't necessarily know exactly what the total mass of whatever it is in the water there, but we know the density of it. And so if that volume happens to change during our analysis, the concentration doesn't necessarily change unless we add a different fluid. And that makes these very portable and easy to use when we're doing analyses of fluids and trying to draw on theories and develop general intuitive understanding of how fluids interact with the environment. So in today's lecture, we covered three important things that form the basis of our definitions of fluid properties and then ultimately our analyses of fluids as we move toward the semester. The first one was the continuum approach, where instead of describing all the individual molecules, we describe a mass, a bulk of fluid, and describe properties that define what the interaction of all those molecules really do end up relating to. Second thing was an equation of state, where we talk about how a fluid at a particular point in time has particular properties, and those properties can actually change when temperature, pressure, or other environmental variables change. And then third, we talked about extensive versus intensive properties. We said that we don't really use extensive properties in fluid mechanics, and that we use intensive properties almost exclusively because they're portable, especially when we start talking about some of the theories and analyses that we might want to take to other situations, and we want the ideas to remain the same without changing. So in the next video, we'll talk about the first fluid property, and probably one of the most important, density.